Good day, cast from 2021 conference attendees. Our presentation today is about two channel restoration projects on Fountain Creek with a focus on the bank stabilization techniques used. I'm Dan Barr with Matrix Design Group. I was the project manager for the planning, design, and construction phases of the Barr Farm projects. The project was guided by Graham Thompson, Senior Vice President and Director of Water Resources for Matrix. The projects were funded by the Fountain Creek Flood Control and Greenway District and is one of several projects that the district has completed on Fountain Creek. The Matrix team in the Colorado Springs office led the projects. The team included Aaron Sutherland, Jordan Becker, and Jeff Batiste, who is now working for the Mile High Flood District. The landscape architect for the team was THK Associates. Matrix has partnered with Kevin Shanks and Julie Gamick of THK on many projects in Fountain Creek that have guided channel restoration efforts. The general contractor was Sun Construction, and Total Terrain was their landscape subcontractor. Netty Enterprises supplied large quantities of erosion control fabric, and Chaparral Construction provided large wood materials. The rock was provided by TZEC Heavy Equipment. The Fountain Creek watershed is 930 square miles at its mouth where it joins the Arkansas River. It flows approximately 60 miles from the top of Pikes Peak at elevation 14,115 feet to the Arkansas River at an elevation of approximately 4,600 feet. The climate in the watershed is semi-arid, and the creek is susceptible to flashy flood events that reach their peak flows within hours. Its sandy bed material is very mobile, allowing the creek alignment to shift significantly during flood events. The Barr Farm projects are located on the lower reach of Fountain Creek, approximately 11 miles from the Arkansas River confluence. The Barr Farm projects are located between I-25 on the west and Overton Road on the east, approximately 1 mile south of the Pinion Road Bridge in Pueblo County, and involved the realignment and stabilization of almost 2 miles of Fountain Creek. The Phase 1 realignment is shown as orange, and the Phase 2 realignment is shown as red. Phase 1 was completed in August 2019, and Phase 2 was completed in June 2020. Channel migration caused 25 to 30 foot cut banks in the Phase 1 segment, and similar conditions were created in Phase 2. A watershed assessment of river stability and sediment supply analysis using Dave Roskin's methods was completed on the lower Fountain Creek. This analysis created a list of high priority projects that included the Barr Farm segments. Large annual sediment loads to Fountain Creek was a key factor in determining their priority. Other factors that pushed these projects up the priority list were the loss of Barr Farm productive agricultural land, the loss of riparian habitat, the loss or utilities being at risk, communication and gas lines were relocated in Phase 1, power lines were at risk in Phase 1, and high pressure gas line was at risk in Phase 2. Overton Road was relocated after a significant segment of the road was washed out. The design process is very similar for projects along Fountain Creek. They include establishing design flows, a geomorphic analysis that includes a time series photo analysis to look at historic migration, the analysis of reference reach data resulting in a departure analysis, channel realignment to create a stable landform. The establishment of a stable landform, in addition to bank stabilization, are probably the two most significant aspects of channel restoration on the creek. And a sediment transport analysis ensures that sediment loads entering the study reach are passed through. Sediment transport analysis is also key to determine cross-section dimensions and channel slope. A hydraulic analysis using HICRAS contributes to determining cross-section dimensions, provides velocities and shear stresses, provides scour depth calculations, channel slope, and flow depths. Bank stabilization, which is the main subject of this presentation, is based on material selection, hydraulic conditions, and cross-section geometry. Revegetation is typically accomplished using native riparian and upland seed, soil amendments, erosion control fabric, willow stakes, and cottonwood poles. Permitting was done under a Corps of Engineers nationwide 27 permit, and a floodplain development permit was received from Pueblo County. The design flows were determined from gauge data at the USGS gauge near Pinion, located approximately 1.5 miles upstream of the projects. The design flows for the project were 33,300 CFS for the 100-year flood, 7,000 CFS for the 5-year flood, 2,900 CFS for bank full flows, and 119 CFS for base flows. Based on the HICRAS analysis, typical hydraulic conditions were a 100-year velocity of up to 15 feet per second within the bank full channel, a 100-year velocity of 3 feet per second in the floodplain, a 100-year flow depth of 8 feet within the bank full channel, a 5-year velocity of 2 feet per second in the floodplain, and 100-year shear stresses of less than 2 pounds per square foot. The Phase 1 realignment required a significant adjustment of the channel to create a more stable planform. This slide shows the original alignment on the underlying aerial photo and the design alignment in blue. Phase 2 also required a significant realignment to bring the planform to within reference reach parameters. The design cross-section was very similar for the two phases. Differences in the cross-section dimensions were due to a small change in the channel slope and to integrate the cross-sections within the surrounding floodplain and landforms. The expected scour, depth of scour in the bends is a very important parameter for design of the bank stabilization. Various methods were applied at multiple locations within the project reaches to calculate scour depths. These included Thorne's, Maynard's, and the National Engineering Handbook Best Fit method. Scour depths were calculated to be between 6.5 and 7.6 feet on Phase 1 and between 4.7 and 8.2 feet on Phase 2. A 100-year scour depth of 8 feet was selected for both phases. The primary material selected for bank stabilization on Phase 1 was soil riprap. The average depth of flow in the Phase 1 bends was 8.2 feet and the average velocity was 13.1 feet per second. The Urban Drainage and Flood Control District, or Mile High Flood District, the U.S. Army Corps of Engineers, and the Federal Highway Administration HEC 15 methods were used to calculate the required riprap size. The calculated D50 varied from 0.38 feet to 7.2 feet. A value of 2.7 feet was estimated using an extrapolated value from the Urban Drainage and Flood Control District method. A D50 of 3 feet was selected for design. Sourcing the large D50 riprap required coordination with the quarry operator and a custom size distribution, which was developed with a D100 of 4.5 feet. The soil riprap was placed on the straightways, approaching the bends, within the bends, and in keys at the upstream and downstream end of the bends. Soil riprap design included a D50 of 3 feet, placement of 8 feet below the final bed elevations, placement 3 feet above final bed elevations in the straightways, A 1-foot wrapped soil lift placed on the bends to allow for super elevation of bank full flow, a thickness of 6 feet, 2 times the D50, and placement on a 2-to-1 bank slope. Installing soil riprap 8 feet below bed levels in an active alluvial stream bed requires significant dewatering efforts. This photo shows a completed riprap installation on a bend with 1-foot wrapped soil lift cover to support native seed establishment. These photos show the condition of the soil riprap bank stabilization 2 years after completion. Design of the large wood bank stabilization for Phase 2 was a very different process from the soil riprap design in Phase 1. Several reference documents were researched to support the design, but the critical reference was Technical Note TN 103.1, published by the U.S. Forest Service National Stream and Aquatic Ecology Center, authored by Michael Rafferty, PE, in 2016. With the technical note TN 103.1, Mr. Rafferty published an elaborate Excel spreadsheet design tool. The spreadsheet provides an analysis of forces and momentums based on user-defined configurations. The spreadsheet provides a framework for evaluating multiple design parameters and structure configurations. Developing a large wood structure configuration is an iterative process between foundation logs and root wide log sizes and placement. The spreadsheet provides a series of force and momentum calculations identifying the locations for each. The key result provided by the spreadsheet is the safety factor calculation for the various forces and momentums compared to the target safety factors. Key design factors for large wood structures include wood longevity related to tree species, saturation, and anaerobic conditions, design discharge at an appropriate level of risk, extent of bank stabilization, hydraulics, channel geometry, log dimensions and orientation, layout and spacing of logs, soil characteristics, depth of scour, anchoring method, and target safety factors. This free body diagram for the spreadsheet tool shows several of the input parameters and forces used for a typical single root wide log and provides an idea of the complexity of the spreadsheet calculations. This construction detail shows the foundation logs supporting the root wide logs and the spacing and orientation of these structure elements. Logs were a minimum of 12 inches in diameter and 30 feet in length. Foundation logs were set at 60 degrees from root wide logs on a 20-foot spacing. The top of root wide logs were set at the level of channel base flows and 15 degrees into the direction of flow on a 5-foot spacing. The placement of the large wood structure below the level of base flows is a key aspect of the design. This ensures that the logs become saturated and helps to create an anaerobic condition, which is expected to preserve the logs for decades. Root wide logs were embedded at least 26 feet into the banks, and root wide logs were anchored to foundation logs at each intersection with a number 6 rebar. To complete the bank stabilization, wrapped soil lifts were placed on top of the large wood structures. This slide shows a construction detail for the wrapped soil lifts. Heavy coir wrap 1200 wrapped soil lifts provide stream bank stability for 3 to 6 years while vegetation is established. The wrapped soil lifts were 1.2 feet in height. Willow stakes were installed between the lower wrapped soil lifts and through the upper wrapped soil lifts into groundwater. The top level of wrapped soil lifts was 1 foot above the bank full flow level on bends. These photos show the condition of the large wood stabilization in Phase 2 1 year and 2 months after construction was completed. Comparing costs between Phase 1 with soil riprap bank stabilization and Phase 2 with large wood bank stabilization, Phase 1 cost approximately $1 million more overall, even though the length of the project was 1,725 linear feet shorter than Phase 2. We have not previously discussed it, but a large wood structure was also installed on 800 linear foot bend in Phase 1. If all of Phase 1 was constructed using soil riprap bank protection, the Phase 1 project costs would have been higher. Even so, the cost difference between Phase 1 at $5.6 million and Phase 2 at $4.6 million was due to the soil riprap bank stabilization. The overall cost per linear foot for Phase 1 was $1,308, and the overall cost per linear foot for Phase 2 was $768. Comparing only the large wood bank stabilization elements of the two phases, including wrapped soil list, the cost was only 30% of the soil riprap bank stabilization cost. Comparing the two approaches to bank stabilization, there are several aspects of the design that are the same. Determining design flows, completing the geomorphic analysis, and the bank design hydraulics are the same. However, there are key differences that need to be considered. Design of the large wood structures require a specialized large wood stability analysis. One of the most critical considerations is the availability of large wood material, especially in the numbers required for almost 2 miles of stream bank. We investigated more than 20 potential sources for the large wood material and was fortunate to acquire the logs from the Spring Creek burn area through Chaparral Construction. Access to the burn area was a factor also because fall weather can hinder harvesting operations. However, fall is the optimal season to work in the Fountain Creek stream bed to avoid higher stream flows. Contractor experience should be considered. Placing riprap bank protection in a stream bed are well-established skills. However, the various materials and sequencing required for the large wood installation requires skills that some contractors may not be familiar with. The level of dewatering required for the two techniques can vary significantly due to the depth of the installation, especially in alluvial stream beds. The timing of the bank installation is more critical for the large wood structure because harvesting and planting of the willow stakes is optimized between the late fall and early spring months. Of course, the lower cost of the large wood structure can be a significant consideration. There are several aspects of our channel restoration efforts on Fountain Creek that deserve a more in-depth discussion, but this presentation focused on one of the most important elements of channel restoration, bank stabilization. We hope you found this discussion of the soil riprap and large wood stabilization techniques on Barr Farm projects informative and interesting. Our contact information is shown on this slide. We would be happy to address inquiries regarding the Barr Farm projects or to discuss how Matrix Design Group might help you on other projects.